For this video, I will demonstrate how to use HLM to graph results from the different models that you're likely to run based on research questions that you might have. For this example, I will use data from the high school and beyond example that's located in the textbook by Rodebush and Breich. And you'll notice that the first model that I'm going to demonstrate here is the unconditional model, where I have math achievement as the dependent variable with no predictor variables at level 1 or at level 2. Now I've already gone ahead and run this model, and so I'm going to show you the output. And so the output, the main part of the output that we're focused on here is the grand mean. So this is what has been calculated by the model based on the data that's available, based on the data in the data set. And so we can see that the grand mean is 12.63. And this grand mean is across schools. Okay. And we also notice that we have substantial variability, or a significant proportion of variability around that grand mean. And so we have the grand mean across schools, and we have significant variability associated with that grand mean. And so what we need to determine, and what we've determined already, is the variability in math achievement, or the explanation of variability in math achievement. Is that due to individual schools, or is there substantial contribution of between school variability? And so when we form the ratio of within school variability in math achievement based on socioeconomic status to within school variability in math achievement, we see that about 18% of the variability is explained by between group or between school differences. So we have to account for that in our multiple regression analysis. And so this is why it's important for us to use multi-level modeling to take that nested structure of the data into account. So what I'm going to do now is really show how variability around the grand mean is represented graphically by the 160 schools that are involved in the study. And so I can go to File, and I can go to Graph Data, and then I can go to line plots and scatter plots. And so on my x-axis I have SES, and in my y-axis I have math achievement. And so I can create a scatter plot of the data. And so this scatter plot shows quite a bit of variability around SES and math achievement. So you can see that we have schools that have high socioeconomic status and high math achievement, and then we also have schools that have low socioeconomic status and low math achievement. So this is an indicator that we do have variability between schools that needs to be accounted for when estimating our models. Another way we can look at the data is to look at it by school. So sector, in this case, 0 is public school and 1 is private school. And if we graph this, we can see that the Catholic schools that are considered sector 1, you have more of those schools that have high SES and high math achievement versus the public schools that have low math achievement accompanied by low SES. So we can kind of see them separated out. The other thing that we can look at is we can look at individual schools. And so I'm just going to use the first 10 schools to do that. And I can go OK. And so what this does is it highlights the public schools versus the Catholic schools. And then it also allows me to get an idea of the relationship between SES and math achievement for each of these schools. And we can see that in this case, at least for this school, which is a Catholic school, they have higher math achievement accompanied by higher socioeconomic status. Where if we look at this school, this is a public school, it has lower individuals with lower SES accompanied by lower math achievement scores. Now what we'd like to do is look at variability in the socioeconomic slopes by math achievement. In other words, do slopes vary across schools? And so I've run the model, and our results, again, we show our grand mean is 12.63. This has decreased some because we've added socioeconomic status at our level 1 as a predictor variable, so it's explaining some of the variability in math achievement. And our slope coefficient is 2.19. So that's the grand mean of all slopes across the 160 schools. But the question is, do slopes differ across schools? And we can see that there is quite a bit of variability in the fixed effects, but really we see that here. So we see our slope variability is significant at 0.003. So we would expect to see a variability across the slopes when we graph our data. So I'm going to go ahead and do that. I'm going to go to File, Graph Equations, Model Graphs. Then I'm going to put SES in, and then I want the entire range. And I'm going to move this up, and then I'm going to go OK. So that gives me the mean for the slope across all schools. Okay, my intent was to show the variability, but I was going to show this model next. So let me go back and start over again with my graphs and go to File, Graph Equations, and I'm going to go to level 1 graphing. This is the one I should have picked originally to show variability across the slopes. And I'm going to pick SES, and I'm going to use all 160, and then I'm going to go OK. So this model shows me the slopes, or the relationship between math achievement and SES and their slopes for all 160 schools. And you can see that the slopes are different. You have some that are sort of accelerating this way. You have some that are flat. So the slope variability across these schools is different. And the other thing we can do is we can do it by sector. So this shows you in red what the slopes are for the Catholic schools at sector 1, and the slopes are for public schools. They look similar, but there is some variability across those slopes as indicated by the significant variance component presented in our HLM output.